Welcome everyone, my name is Sebastian and today I would like to talk to you about our work on the estimation of causal effects in the presence of unobserved confounding. In this work, our goal is to understand the cause and effect relationship between regional atrophy of the brain and cognition. Intuitively, you probably would take a collection of brain MRI, segment them, and fit a regression model to estimate to which extent regional volume and thickness measurements predict cognition. However, this would only provide us with a measure of association, but what we really want is a measure of causation. In particular, we would like to answer what-if questions. For example, what is a patient's cognitive score would the hippocampus volume be X instead of Y? Let's consider the simplified example on the right, where we want to estimate the causal effect of hippocampus volume on the ADA score, which is a measure of cognition. The graph represents the observed data distribution over age, hippocampus volume, and the ADA score. Arrows represent dependencies between the variables. Here, the ADA score depends on the hippocampus volume and age. If we train a machine learning model to predict the ADA score from hippocampus volume, we estimate the following conditional probability distribution. The probability of ADAs conditional of hippocampus volume at X. However, machine learning alone is not going to be sufficient to estimate the causal effect. To infer causal effects, we need to do causal inference instead. Causal inference is about answering the what-if question. What is the ADA score would the hippocampus volume be X? In technical terms, this is called making prediction under intervention and is indicated by adding a do operator to the condition. The resulting probability distribution is called the post-intervention distribution. The post-intervention distribution can also be represented graphically by removing all incoming arrows to the hippocampus volume node and fixing the hippocampus volume to the constant X, as shown in the figure on the right. What makes causal inference challenging is that usually the post-intervention distribution cannot be observed. In particular, the conditional distribution a machine learning model estimates and the post-intervention distribution are not the same. Only if we perform a randomized trial where hippocampus volumes are assigned to patients randomly, association would imply causation. Obviously, this is not possible in neuroimaging. Instead, we need to rely on observational data and make untestable assumptions about the data generating process. One such assumption, that's the main focus of our work here, is that there is no unmeasured confounder. In the graph on the right, age is confounding the effect of hippocampus volume on cognition, because age is a curve of both hippocampus volume and cognition. The no unmeasured confounder assumption is problematic, because Alfaro, Almagro, and colleagues already identified hundreds of confounders just related to the image acquisition alone. Therefore, we expect this assumption to be violated in most neuroimaging studies. Before we can begin to estimate causal effects, we now need to determine whether the post-intervention distribution can actually be estimated from our observed data. This is called identifiability. In contrast to our work, previous neuroimaging studies only focus on a scenario where all confounders are known and have been measured. We can distinguish two main approaches that have been used to account for observed confounders: regress out and inverse propensity score weighting. In regress out, one tries to predict a measurement from the confounders only, and then the resulting residuals are used in another model to estimate the effect on cognition. This is the approach that is most commonly used. Methods differ in terms of the confounders they correct for and the regression model. Mostly people correct for age and gender, but some works also account for imaging site and scanner. The work by Costro and colleagues uses a Gaussian process to compute residuals, the remaining works use linear regression. The second approach uses instance weights to create a pseudopopulation in which the confounders are approximately evenly distributed among the outcomes. Instance weights are based on the conditional probability of the outcome given the observed confounders. Two papers use such an approach. Lin and colleagues estimate the instance weights by logistic regression and use the weights in an SVM. Rao and colleagues estimate instance weight by a Gaussian process and use them in a separate Gaussian process to predict the MMSE score. The biggest concern with all the previous works is that they did not study whether causal effects are actually identifiable from observational data. In particular, most works do not define the causal question and list all the assumptions that are required to answer it. This is concerning because it is absolutely necessary to make additional assumptions when estimating the causal effects from observational data. Therefore, one should explicitly list all those assumptions that are required to answer this question. Our work tries to fill this gap by taking a holistic approach that is based on the so-called do calculus from causal inference. To do causal inference, we have to carry out the following 3 steps. First, we have to define the causal question and construct a causal graph based on the current knowledge on Alzheimer's disease. Next, we need to take a step back and do a combination of careful thinking and do calculus to determine which quantities can and which cannot be estimated from observational data. Finally, we can use modeling to estimate those causal effects that are identifiable. Let's begin by defining our research question. We want to know what is the average causal effect of changes in volume or thickness of a subset of neuroanatomical structures on the ADA-13 score in patients with an Alzheimer's pathological change. The ADA score counts the number of mistakes a patient did during her cognitive evaluation. The condition on Alzheimer's pathological change implies that we are only concerned about dementia due to Alzheimer's and not other forms of dementia. Based on that question and the current knowledge on Alzheimer's, we define the causal graph shown here. The causal graph represents our current understanding of cognitive decline due to Alzheimer's and is represented as a Bayesian network. Nodes are random variables and arrows between them represent dependencies. For instance, the edge from gender to total intracranial volume on the left tells us that gender is a cause for total intracranial volume. Therefore, it captures our knowledge that men and women have different head sizes. For the sake of time, I'll skip the justification for the remaining connections. Please check our paper for details. Instead, I'm going to highlight a couple of properties that are going to become important later. First of all, the effects we want to estimate are marked by red arrows. It's the causal effect of subcortical volumes and cortical thickness on the ADA score. Subcortical volumes are represented by D1 nodes in the graph, highlighted in dark green. Cortical thickness measurements are represented by D2 nodes in the graph, highlighted in light green. Age is a known and observed confounder because it causes both the neuroanatomical measures and the ADA score. From previous work, we know that there are additional confounders beside H2, which we all capture by introducing the unobserved confounder U, highlighted in blue. Equipped with the causal question and causal graph, we move to the next step, determining whether the average causal effect of neuroanatomy on others is identifiable. This implies determining whether the post-intervention distribution, highlighted in red and identified by the do operator, can be estimated from observed data over neuroanatomical measures X and the ADA score. The answer is no, because we would need to account for the confounder U, which we cannot because it is unobserved. If the causal effect is not identifiable, we need to make assumptions to restrict the problem. To this end, I first want to note that we are interested in multiple neuroanatomical measures, X1 to XD, and not just a single one. Moreover, the combined neuroanatomical measures become conditionally independent given their observed and unobserved parents, marked in blue on the right. The key insight is that this conditional independence, which comes solidly from the causal graph, is identical to the form of a probabilistic latent factor model. This has first been recognized in a paper by Wang and Blai from 2019, where they introduce a way to estimate a substitute for the unobserved confounder. Our work builds upon their theoretical results and extends them to the setting where we have both observed and unobserved confounders. We explore 2 approaches to estimate a substitute confounder in the paper. In this presentation, I will only talk about the extended probabilistic PCA though. In our extended PPCA, we express the observed causes as a sum of two terms. The first term, W times that, corresponds to the standard PPCA, which will provide us with the substitute confounder that. The second term, A times F, accounts for the observed causes of X, including the observed confounder H. Putting everything together, we obtain the Bayesian model on the right. We then plug in the observed data, marked in gray, and estimate the posterior distribution of the latent variables marked in white. This will provide us with Z, the substitute confounder, that we will use in the estimation of the average causal effect in place of the unobserved confounder. To prove identifiability of the post-intervention distribution, we need to eliminate the do operator such that only observed quantities remain. Here's the proof that shows that the causal effect of a subset of neuroanatomical measures on cognition is identifiable. First, the causal graph tells us that we need to marginalize over age the neuroanatomical structures we are not interested in and the substitute confounder. Next, we apply three rules from do calculus. This is the crucial step that does result in eliminating the do operator from the expectation. The details are a little bit tricky because it involves manipulations of the causal graph and checking for certain independencies in the manipulated graph. Therefore, I will skip this part. Next, we simplify the formula by utilizing independencies given by the causal graph to eliminate p-tau from the condition. Finally, we approximate the outer expectation by Monte Carlo. Now that we have shown that the post-intervention distribution is indeed identifiable, we can use modeling to estimate the remaining expectation. Since the other score is bound between 0 and 85, we converted it to proportions and used the Bayesian linear beta regression model to do that. While this may appear to be magic, remember that I told you in the beginning that we have to make additional assumptions on the data generating process. Therefore, what we are doing here is very much specific to our particular question and the causal graph. Our proof may not apply to other settings. Instead, you would need to go through the steps of do calculus again to determine whether it is valid for your particular setup. I want to be explicit here and list all the assumptions our approach is based on and also discuss them. The first assumption relates to the causal graph. It needs to be faithful. That means independencies in the graph must hold in the data. For most problems, this cannot be verified based on data alone, and we have to accept this as a limitation of causal inference from observational data. To be able to apply a factor model, we require that the unknown confounder affects multiple brain regions and not just a single brain region. Again, this cannot be proven, but we believe that likely candidates for the unknown confounder are scanner or age related, which would affect the brain as a whole and satisfy this assumption. The next assumption says that the probabilistic factor model needs to capture all neuroanatomical measures well. This one we can actually check using posterior predictive checking. The next assumption is a theoretical one due to the work by Wang and Bly. It holds for a large class of models, as has been proven in the paper by Chen and colleagues. The final assumption is required to estimate the inner expectation of the average causal effect. This positivity constraint holds because we model this distribution by PPCA that uses a normal distribution, and the normal distribution is non-zero everywhere. To quantitatively show that our approach works, we need to use semi-synthetic data, because for real data, we do not know the true causal effect strength. We used brain scans from almost 12,000 patients from UK Biobank and generated a synthetic unobserved confounder and a binary outcome. We compare our approach to the regress-out method that only accounts for the observed confounder age and to the non-causal model that ignores all types of confounders. Finally, we include the oracle model that uses a true observed and unobserved confounder. This provides us with a lower bound on the error corresponding to a scenario where we would have access to all confounders. The plot shows the overall root mean squared error with respect to the true causal effect strengths for varying levels of confounding. For all methods, the error increases as confounding becomes more severe. On the left, the direct effect of neuroanatomy on the outcome is 10 times higher than the confounding effect. On the very right, the situation is reversed and the confounding effect is 10 times higher than the direct effect. The non-causal model, which is the blue line, is clearly the worst. The regress-out model, depicted in orange, performs slightly better, but is still far from the oracle, which is the red line. Our approach based on estimating a substitute confounder via PPCA is marked in green. It is very close to the oracle for low levels of confounding, but the gap increases as confounding increases. Overall, our proposed approach consistently outperforms the regress-out approach across all confounding strengths, which shows that accounting for unobserved confounding is important. Moving on to real data from the Alzheimer's Disease Neuroimaging Initiative. We used 14 volume and 8 thickness measures of 711 subjects. We restricted ourselves to patients that are amyloid positive to specifically focus on dementia due to Alzheimer's. We estimated 6 substitute confounders using our PPCA model. The competing methods are the same as for the semi-synthetic data, with one notable difference: we do not have ground truth. Therefore, a quantitative evaluation is impossible, and we can only provide qualitative results. Here, I'm showing a subset of the results. Please refer to the paper or join the poster session if you want to see the full results. The plot shows the credible intervals of the estimated coefficients for each neuroanatomical measure. The horizontal dotted gray line is at 0 and represents a null effect. The dots represent the posterior mean. A significant effect is marked in black, and an insignificant effect is marked in gray. If the dot is above the dashed 0 line, an increase in volume or thickness contributes to cognitive decline. If the dot is below the dashed line, an increase in volume or thickness contributes to improved cognition. The type of measurement is indicated at the bottom. Thickness measures are marked with a T and volume measurements with a V. There are 2 structures that are significant in the non-causal approach, but not in our approach. Those are lateral orbitofrontal thickness and optic chiasm volume. In particular, for optic chiasm, we believe this to be realistic because atrophy of the optic nerve is unlikely to cause cognitive decline, as its main function is to transmit visual information. The second group comprises regions that are not significant in the non-causal model, but are significant in our model. Of those, accumbens area undergoes the most dramatic change. It goes from a close to 0 effect to a significant negative effect. This appears to be reasonable because the accumbens is part of the limbic circuit, and thus it is vulnerable to degeneration during cognitive decline. I also want to highlight the effect of parahippocampal thickness. In the non-causal models, atrophy is associated with improved cognition, whereas in our model it flips to being associated with cognitive decline. Since parahippocampal thinning is common in Alzheimer's disease, we believe our model would be more appropriate. Finally, I want to show the 2 most important causes of cognitive decline. It is not surprising that those are hippocampus volume and entorhinal thickness. It is reassuring that all models agree on this. But the non-causal models seem to have underestimated the strength of those causes on cognition quite a bit. Overall, our results demonstrate that by ignoring unobserved confounding, we can end up with misleading conclusions, like in the case of parahippocampal thickness or accumbens. To summarize, we showed that unobserved confounding renders the causal effect of neuroanatomy on cognition unidentifiable. We then proved that we can estimate a substitute confounder via a probabilistic latent factor model such that the causal effect becomes identifiable. This requires several assumptions, some of which cannot be verified based on data alone. Therefore, if you want to use such an approach for your data, you have to ensure that all the assumptions also hold in your particular setup. Finally, I want to point out that our code is available on GitHub in case you're interested in applying it to your problem. Thanks for watching.